Okay, so it's my pleasure to introduce to you Thierry Njougouo from the Mathematical Institute of Lucca. And Thierry is, he's from Cameroon. He started in Cameroon and in the University of Chang. And from there, he went to the University of Namur in Belgium. And he worked with Theo Carletti, many of you know him. And okay, and from there he went to Lucca, and now we have him here to tell us about chimera states or networks with high order interactions. So please.
Thank you, Professor Ida, for this introduction. Hello, everyone. I know that you are very tired, so I'm going to be a little bit fast, and I will introduce things in a simple way. So my talk today is about chimera state on a network with high order interaction. I changed a little bit the title because at the beginning I was supposed to talk about collective behavior network with high order interaction. But during the week, I realized that Jesus and also Albert did everything about the synchronization. So I don't know what I will talk about synchronization now. So let's talk about chimera state. What is chimera state? And why chimera state? Where could we find a chimera state, for example? So we use, in this talk, I will introduce things very in the simple way, like I say. So what is chimera state? I think on maybe it was Monday or Tuesday, something like that, Professor Oroji introduced what is chimera state. She showed us this nice picture. What is it was initially what is chimera. So the most important thing here is the fact that you can realize that in this animal we have in the same animal 3 different kind of animal. We have in the head we have we have the head of lion and goat, and the tail we have a snake. So we can realize that in the middle these 3 animals share exactly the same body. So we will say we have a kind of coherence and an incoherence. Coherence is due to the fact that they share the same body. And then let's go to the physics. In physics, what is chimera? Since 2000, and I think it was in 2002, this work is not exactly the same here because I mean something. This term chimera was introduced in physics for the first time by Kuramoto and Batokto, where they proved that if we use a particular kind of coupling, exactly the non-local coupling, we could finally reach to this kind of behavior. We have exactly the coexistence of coherence. Some people like to call it synchronization, and incoherent domain. So that is exactly what we will call chimera state. So now, most of us live with chimera, right? So I'm sure that some people already know about this or see this kind of picture or animal in our house, for example, what we will call chimera cat. What is chimera cat? We obtain chimera cat when we match together 2 types of embryon, for example. And in the skin, we will have different motif or patterns sometimes. So let's show us one picture in the reality. We can realize that here we have a kind of the same color in the skin. And here we have a different pattern. So we will call out, okay, in this domain we have a kind of coherence, and here we have a kind of incoherence. So from this definition, I have a question for you. This card, is it a chimera card? No. If we go back to the course that we already have this week, how we call it synchronized card. Jesus already did, he did everything about synchronization. So we will call this one synchronized card. And so let's now, yes, sorry. So I made something. So here we have a coherent domain, and here the incoherent domains. So now let's show this video. It was, I think, in the course by Albert. He already showed us this video to explain what is synchronization in the metronome. We could also obtain chimera state using the same metronome. So maybe it would work, I hope. Okay, perfect. Perfect. So here we can realize that somewhere we have some metronome that oscillate exactly with the same frequency, and some other metronome that are oscillate with different frequency. That is exactly what we call chimera state, for example. And so this is a kind of a video that we can realize or we can find anywhere. So now let's go back to the topic of the school. Topic is about brain. So I'm not a physician. I'm not expert on synchronization. So here, for example, just want to show you something about chimera. What is the relationship that we can have between chimera state and some neuronal disease, for example, like Parkinson, Alzheimer, and something. And we can see that in this nice paper, that the author point out the fact that the chimera state could be at the origin of some neuronal disease, for example, the one that we mentioned here. There are a lot of work also in the literature where we can find some detail about this. So this is very interesting. I could not explain why. I could not. So this is just to show. So now where we can obtain chimera state? We know to obtain chimera state, we need a network. What is a network? A network is a set of entities that are connected by the link. That is in the case of graph. So if we use some mathematical term, we, as a physicist, we most of the time use the graph theory, the tool from graph theory to encode the structure of our network. For example, the adjacency matrix that we use a lot this week to encode the structure of the network. The structure could be maybe random, scale-free, small word, or regular, something. It depends. So in the case of graph, with geodic interaction or pairwise interaction, we have exactly this kind of matrix. It takes the value 1 if there is a link between the nodes, 0 if not. And then let's switch to this particular kind of coupling. Maybe the first one was introduced yesterday by Albert. This one was used in several talks by Jesus. And we know that, okay, this one particularly is used in the case of mean field theory because the number of links is exactly the degree of the nodes is exactly or approximately the number of the nodes. So this one is the most important one for us. Why? Because to obtain chimera state in the literature, most of the work, particularly the first one from Kuramoto, recommend to use non-local coupling. Why? Maybe because is it very easy to maybe for information to flow or to introduce a kind of I will say kind of incoherence maybe, but let's see. So in this non-local coupling, the particularity is the fact that, okay, we could define exactly the number of nodes that of a neighbor in the left and the right in the case of a ring. So this is the case of pairwise interaction. Very nice. So for this, let's introduce these parts. The chimera state in the pairwise interaction by this work with my colleagues in Cameroon also. We use exactly the pairwise interaction that the non-local coupling that we present. So what we change here? In the node we use the Hopfield neural network that the mathematical expression is already know. And what we change here compared to the one that we all have in the literature is the coupling term. It's non-local, right? But in this black box or blue box, we use the PID. for those who have some experience in electronics or automation, know exactly what is the importance of PID controller, for example, in the case of regulation and or control, for example. So we use it, why? Because with this small controller, we can, in the same way, have a kind of diffusive coupling, could be proportional, integral, or derivative. So it can in some sense, assume maybe control the stability of our network, for example, in terms of collective behavior. So we know that the coupling between two nodes here, in this case, is a current. And using this one, the current here is just the difference of potential divided by the impedance of the component. And so finally, we have this. In this, we have the structure of the network, non-local coupling. And by doing some simulation, we obtain something very nice. This chimera state. We obtain this kind of chimera state. This chimera state, we can also obtain, in some situation, multi-chimera state, even if it's not very nice. But using local order parameter, we prove that here we have a kind of incoherence, and here we have a kind of coherence. But the motion oscillates during time, on time. And finally, I put this image just because I want to show some kind of synchronization. And here we can see that, okay, using, for example, in this case, the most important thing to know is if we use this component individually, it will be very difficult to reach chimera state. And even if you could reach the chimera that you will obtain, it will be a very weak chimera. And then if you want to obtain something very stable, like here, for example, you have to combine these three coupling at the same time. Then, this is very nice. It proved that, okay, we can obtain chimera state in the case of pairwise interaction. That's nice. Nice. So now, here, phi is just the phase, because of the node, exactly. Sorry about that. So now, in the previous slide, we proved that, okay, we could obtain chimera state, or to obtain chimera state, it's recommended to use non-local coupling. That's true. But the non-local coupling is not the only topology that we could use to obtain chimera. For example, in this work, with my collaborator, we showed that using a kind of intermittent coupling, we could also reach, in some case, synchronization or chimera state also. Why intermittent state? Because of numerous applications in the real world. For example, we use it most of the time when we want to call. If we want to call somebody, for example, in the United States, not using WhatsApp, for example, direct call, we need to have the amplifier, because the signal, if you don't have amplifier, the signal will die after some certain distance. And then we use this GP like the threshold of the distance that we could use. It's not really a physical distance in the case of chaotic oscillator, but we use it just to approximate the situation. And here, this is an evolution of the coupling and also the error. We can see that, okay, using this kind of coupling, we can, in this scenario, for example, have the coupling instant when the error is less than the threshold. If the error is greater than the threshold, we will have some uncoupling state, for example. And then, using this, we apply it on this system. And we can realize that, okay, here is the Lyapunov, the transphasor Lyapunov. The black domain shows where we can obtain the synchronization, and the white one is where the synchronization is not realized. And then we can observe that, okay, to reach the synchronization, we just have to increase the threshold. That's right, because if we increase the threshold, we increase the probability to have connected system. And then we increase the probability for the system to be synchronized in a certain time. And then we also, I don't put the result here, we also in some do the circuit of this, and we obtain something really, really similar to this. With electronic circuit, we also reproduce exactly something in the very similar to this result. So we use exactly the same thing, but in a network of linear system. And finally, using this kind of intermittent coupling, we reach this kind of pattern. This is chimera state also. Or in this case, this is multi-chimera state because we have two domains of coherence, for example. And then it proves that we could obtain chimera state, not only with non-local coupling, but also with another type of topology, for example, or coupling. And for those who are interested in this field, we can check this book by Anna Zakharova. It's a very nice book in the field of chimera state. And then, very nice. So in this first part, we use pairwise interaction and show that, okay, with pairwise interaction, we can obtain chimera state. And then, let's switch to the higher order interaction. Why higher order interaction? During this week, we have a lot of presentation about brain or synchronization. In most of these presentations, they use pairwise interaction. But I have one question. In a real scenario, do you think that interaction is really pairwise? Really difficult. Even if we have a very good result, sometimes we have some limit due to the type of interaction that we use. And we could see this one, for those who have some experience in epidemic spreading, for example, you will realize that when you use pairwise interaction to build a model, and when you use higher order interaction, the result in some cases are completely different. Higher order interaction is more accurate than the pairwise interaction. It's not to say, okay, the thing that we are doing with pairwise interaction is wrong. No. Pairwise interaction has this advantage that, okay, using it, we have a very, mathematically, we have a very simple model in some situation. Or with higher order interaction, we have to think about, okay, how the nodes interact. And that's exactly the question that I want to ask to you. In the case of brain dynamic, if it's real that chimera state is the origin of some neuronal disease, and we want to approach one solution, the first question that I will ask is how the node or how the neuron interacts in our brain. This is the first question. And then if we have solution to this question, the next one could be, okay, we could build some kind of network or some kind of topology, and then we could have something more accurate. So in the case of higher order interaction, here we will have two. We will have simplicial complex and hypergraph. What is simplicial complex? In the first part, we show a kind of pairwise interaction. In the simplicial complex also, we could have in the same the pairwise interaction because we decompose the higher order interaction in terms of pairwise and a triangle and so on. And in this case, when we have just an isolated node, we call it zero simplex. If you have two nodes, you have one simplex, two simplex if you have three, and three simplex if you have four nodes. But in this case, when we use it in a network, we have to take the contribution. If you have, for example, four nodes, we have to take the contribution of each pair. We have to take the contribution of each pair, of each triangle, and if you want to take if you want to use the wall form, you have also to take the contribution of a tetrahedron. And the second type that I will present here is hypergraph. Compared to the simplicial complex, in the case of hypergraph, we take the whole like one set, for example. Why one set? Because in the case of hypergraph, we could have interaction with more than two nodes. In the case of graph, if the links can connect two nodes, and in the case of hypergraph, the link can connect more than two nodes. Like here, for example. We have this one, the blue one is the node, and we can have this yellow domain, we will call it hyperreach. And in the hyperreach, we can put whatever we want. in terms of node or in terms of number. So let us use this, particularly this hypergraph in the next step. So this is the three forms that we have until now: the pairwise interaction, hypergraph, and simplicial complex. So in the next step, we will focus on this. For our chimera state, we will do a kind of comparison when we use pairwise interaction and when we use hypergraph. And we will compare the result of the two types of network using exactly the same system, the same coupling strength, and the same form of coupling. Yes? Maybe you have to use. Okay.
Like the question is in the hypergraph, when you are trying to, when you draw the hypergraph from this network, why don't you have any of these graphs between, let's say let's start counting, 1, 2, 3, and the fourth node on the top? Why don't we have it between the third and the fourth node on the top? Why don't we have any connection?
This result is not mine, but I will show you something similar.
Okay.
I do a kind of, in the next slide, I will show you a kind of comparison. Right. Okay. Okay. This is just to show the different kind of topology of interaction that we could have. So let's move to the hypergraph. And then for this scenario, for this kind of scenario, let's consider three articles by different authors. So in the first article that we call here, small a1, we have three authors, named capital A, B, and C. So here, we suppose that, okay, these three authors write this paper. The second article was written by B, C, and D. We have the second IP average. And the third article was written by C, G, and E. We have these three hypergraph, just to build a kind of interaction between the authors. So what we want to do here is to do a kind of, to build the pairwise interaction of this hypergraph. So the pairwise interaction is just a projection, because in the hypergraph, we need to have the interaction in the same time. It's simultaneous. In the same time, so in the first hyperage, we will have this one. In the second one, we will have this one. And in the third, we will have this. Right? Is it okay? Perfect. So now, yes. About in the case of hypergraph, we will not anymore use the adjacency matrix, but we will use tensor. That we have exactly the same property that like the adjacency matrix that we have in the case of pairwise interaction. The only difference here is the fact that we increase the number of nodes that we will have in the hyperage or in the length. So this is already shown in several talks. So let's change a little bit the story. The second article in this one was written by, let's say, B and G. C is not anymore the co-author of this paper. So we have two different scenarios. And then let's build the pairwise interaction or the projection of these two hypergraph or these two networks. We have exactly the same, right? Do you think that is normal? That if we start with two different hypergraphs, we will end up with the same graph in terms of projection? It's not normal. And that's why we are saying the graph representation in some real scenario has some limits. We have to move to higher order interaction if we want to do something more accurate. So let's go to the first part where we can apply this. It's not my paper. It's just something that I took in the literature. And the author show that if we use higher order interaction, in the case of to measure some signal in the brain. Higher order interaction is more accurate than the one that the result that we obtain with pairwise interaction. That's correct. We already proved it with this small example. And then let's move in the case of chimera state. This model, we already know it. Jesus uses a lot of time here, also Albert. And then what we want to do here is to use pairwise interaction, not pairwise interaction, simply shell complex to model the interaction between nodes. So as I already mentioned, in the case of simply shell complex, we need to use also the contribution of pairwise stem. This is the first one. We have the contribution of three-body term, and so on and so on. And then, this paper by Dibakar and collaborator show that if we use this high-order interaction, they promote the chimera state in the network. That maybe is true. I'm not saying the paper is wrong, no. If we observe here, for example, we have this 2D representation. This domain is the coherent domain in coherent one, and here we have the chimera. Let's suppose sometime that we switch the pairwise interaction to 0. So if we switch it to 0 here, we will end up in the case of incoherent domain. It seems that we will never reach chimera state. Let us now switch off the three-body interaction. If we switch out, we put it at 0, we will end up with a kind of coherent state. So it means that to obtain chimera in this case, we need the contribution also of pairwise interaction. But this is not a chimera state obtained in the pure high-order interaction, because without pairwise interaction, it will be very difficult to obtain chimera in this work. That's why we try to do in this paper to build a model or a structure that uses only pure pairwise interaction, in the case of hypergraph, to obtain chimera state. It's clear that it is very artificial also, but we obtain chimera state finally. So what we did is, okay, was if we consider that a node, the dynamics of a node, is defined by this, in a very general form, by this, this equation, where x dot equal to fx is the isolated system. And then if we add the interaction term, we obtain this one. So this I, A is the tensor, adjacency tensor, is epsilon is the coupling strength, and here H is the coupling function. We try to use something diffusive-like. Why we use diffusive-like? Just because we want to do, at the end, we want to do a comparison between high-order interaction and pairwise interaction. So, using this one, we choose a kind of non-local and non-regular. The word non-local, we already know it, because we present here a kind of non-local coupling in the case of pairwise interaction. And then we use here in this form because it was very difficult to use a non-local and regular topology, exactly like the case of pairwise interaction. So we build something non-local and non-regular. Non-regular just because the degree, the hyper degree of a node differ from one node to another one here in this case. So this is a projection of this network. In the case of four-body interaction, we obtain exactly this network. And then in each node, we use, yes, in the case of four-body interaction, exactly, we use as a coupling function this one, I will skip. Yes, this function. x1, x2, x1, x2, x3, just because we want to choose something diffusive-like. And then, in the case, to preserve the degree of nonlinearity, we use in the case of projection, just x3 because the nodes are exactly the same. So we have x power 3. And then, in the H node, we use this Sword-Landau model. It's not Kuramoto, at least. And we build exactly, finally the system that we will obtain is this one. This is our isolated system if we fix epsilon equal to 0. And then we obtain this one. And make sure that this one is not the case of, is not the all-to-all coupling. Because all the possibility or all possible permutation that we will have is encoded in this A. So it's not the all-to-all coupling. And then, yes.
Sorry, but I want to understand. So the point is, what you call higher order interaction is because the interaction between two nodes, you have to have, in those, let's say, the hypergraph or there, you have more than two. And the difference is because they cannot be simply diffusive, just the difference between the two. They have to have a more complicated function of all those nodes. Is that what you call, I don't understand what is called higher order interaction.
No, here in this case, higher order interaction is just due to the fact that the interaction between the node in the same hyperreach has to be at the same time. And then this kind of interaction could not be linear. So we need a nonlinear function to define this kind of interaction that we will have inside the same hyperreach. Diffusive, mathematically, maybe the property of diffusive function maybe could not be respected. That's why I'm calling it diffusive-like. But you can change, if you want, you can change the function. You can use the form that you want. But if you want to preserve the higher order interaction,
the function cannot be x1 minus x2.
No, the function cannot be x1 minus x2, just like that, because it's a linear function.
Okay.
It's a linear function. If you use just x1 minus x2, it's a linear function. And the higher order interaction, the simple example that I can make.
The question is the function. Do you call higher order also if you have diffusive type of interaction, but you have more than two links in a node? What do you call that? Also, because in one of the figures you had only two in each of them, and you also call it a higher order, but you also call, but you had, what was? You had many. I'm getting confused with how many links. Does it have to be with the number of the links or with the type of the function that you have in your link?
In this case, yeah, the type of the function or the power of the function is relative to the number of nodes that we have in the hyperreach. In some scenario, we could have two nodes in one hyperreach. This is just to make sure that in terms of dimension, we have something exactly similar. So if you have two, you will do you can make something with power 2 if you want. And you have to make sure that with the node in another hyperreach, for example, that is more than 2, the function or the definition will remain true. Okay, great. So finally, we have this. Okay. The links. No, here. Yes. Yes. For example, I think in this case, it will be a bit complicated. That's why, in the case of Kuramoto model, they like to use simplicial complex instead of hypergraph because of this type of coupling that we have. So let's move to the result part. So we just simulate these two type of equation. And in the case of higher order interaction, with 4 nodes in each hyperreach, you obtain something where we can identify 2 different domains. Here we have coherent domain, and here we have incoherent domain. So in the case of projection, we have something that are very coherent. So what does it mean? It means that, okay, if we use pure higher order interaction, we obtain chimera state. If we use pairwise interaction, even if we choose the coupling function exactly the same type, we will not reach the chimera state. So it means that higher order interaction in some scenario brings something more than pairwise interaction. So let's move, because this one was just a time series of one variable, x of y variable of the system. And then let's move, because we want to know, okay, this is a chimera. What type of chimera is this one? It's very difficult to answer with this one. It could be amplitude chimera, phase chimera, or something. So to answer to this question, we use this transformation of Stroud-Landau model. And finally, we'll use this z variable, where a is the amplitude, omega is the frequency, and theta is the constant phase. So in the case, if the chimera that we present previously is a amplitude chimera, we will obtain this, we will observe this incoherent domain in the amplitude. If it's a phase chimera, we will obtain this incoherent domain in the phase. So let's directly move. And then for the same simulation, using just this transformation, we can observe that, okay, the amplitude and the frequency remain exactly the same. We have something that is smooth. So it means for the oscillator that belongs to this incoherent domain, the amplitude remains exactly the same. But the only thing that is modified here is just the phase. So this is a phase chimera. So we do the same thing. We did the same thing with the click or the pairwise interaction. We obtain something that this one we could not call it chimera state. This is just a coherent state. It's not synchronized state, but a coherent state. So let's modify or decrease the number of nodes in the network, fix the coupling strength, and then observe. If we start with 408 nodes, we still obtain chimera state. If we switch to 102, we obtain chimera state. Here, with 48, we obtain chimera state, and here with 24, it's something that we could call chimera state, but it's not really a strong chimera. So what does it mean? It means that, okay, even if we play with a number of nodes, when we increase the number of nodes, we increase the probability to get chimera. And then let's do a kind of a comparison between, not with the number of nodes, but with the size of the hyperreach. Now, what happens if we change the size of the hyperreach? We start with 3. So inside each hyperreach, we consider 3 nodes. And then here, we could not call it chimera state, because it's something that seems to be very, very coherent. This is a higher order interaction. This is the pairwise interaction. And here we know that we can observe that it's coherent state. And then if we switch to 4-body interaction, we obtain something. We obtain chimera in the case of our high order. Here we obtain chimera with 5-body. 6-body, we obtain chimera. But in every case, it's not possible to reach chimera state with pairwise interaction. And that's why we think that, okay, this was a contribution for us. So chimera state, we could obtain it using pure higher order interaction. And in some scenario, is it also a good way? Higher order interaction is a very good or simple way to control this chimera state, for example. And that's why in this work by Ricardo and collaborator, it's one of my collaborators, he proved that, okay, instead of using, because he used a pinning control to have or to control the chimera state. So In this scenario, he considered that the whole system starts with exactly the same initial condition. Okay. The same initial condition, and then using the pinning control. It can be adaptive, and it could be additive pinning control, or in some case, parametric pinning control. We obtain something like this. If when he used higher interaction, we obtain this chimera state, and here, in the case of pairwise interaction, sometimes we obtain chimera state, but it's not, this chimera state is a kind of transient chimera state. So, I will skip this one because it's present exactly the same one. And so here, in this last result, he considered exactly the same number of nodes, and then he just changed the number of nodes in the hyperreach. And then we can see that, okay, if we increase the size of the hyperreach, we will decrease the number of nodes that we need to control the whole system. In the case of pairwise interaction, it could be very difficult to have this kind of result. So finally, we show that, okay, if we use higher interaction, we could improve some result. We could also build a kind of chimera state. We could control this kind of chimera state. And in comparison with pairwise interaction is something that could not really be, I will not say relevant if you do this kind of comparison. So higher interaction for us is the best until now. So I would like to thank my collaborators, who's not here. So Hilda is here, okay. So Hilda, I don't know if I could have just some few seconds to make some publicity, but without money. Okay, thank you. So I would like to invite people who are interested. We are organizing the next edition of PNLG in Italy, in Lucca. It's a very nice city. If you are interested, you can just scan the code or click on this, or using this link to apply. Thank you very much.
Okay, thank you, Thierry. Very nice talk, thank you. Questions?
They are very tired.
Yes, Ricardo. I think it's off.
You do any of this in continuous space, or you always need to be working on discrete space?
Until now, we didn't pay attention about in the case of discontinuous studies. Maybe it could be a nice thing to explore. Thank you.
Thanks.
Any other question? Well, thank you very much. I have a question, but it'll take too long to answer. So, thank you very much. We'll talk about it later. Well, the next speaker is